every time I think I'm done, there's just always that one more thing. I was reminding of Columbo here. So I want to test the interrupts from this chip before I go and spin the board again. So I'm going to have to put in a diode and a header here. And we're going to have to code up a quick test app to make sure that this thing does what it's supposed to do. And I can recognize these mode 1 interrupts on the Z80. Even if that's not what I ultimately use, it's designed. Let's make sure it works. Now for the diode, we have this lovely 1N4305. Apparently I have a good 200 of these lying around, small signal. Obviously this is a Jamco label, if you're not familiar with that. Major brands, you just order a diode and they give you whatever they've got. This is fine. Jamco usually has like bargains on buy 100 for $1 or whatever over the years. Okay, and then we have nice gold plated header to go in here. Ooh. Yeah, I didn't see that coming, right? Oh, that's actually very close. You can sort of see it's a little bit crooked there. Well, that's fine. It's good enough for our needs. I should move it closer to the 138 is what I should do. I wonder what the courtyard settings are on, how do I get some light on there so we can all see it on KeyCAD. Yeah, that's just crazy close to this header here. All right. I will get over it, however. This here. Come on. I bent this a little bit long. I think I might be able to pull it in there. Oh, no, it's actually pretty close to feeling pretty good in there. Okay, not bad. Of course, the diodes are polarized. You need to make really sure the stripe is on the right spot. Yes, it does appear the stripe is on this end, as is drawn with the silk screen. And if memory serves, this end of the diode on this side is what runs over and connects to the interrupt pin over here, and this end goes into the chip, and when it asserts the interrupt, the chip goes low, and the ground side has to be on the stripe end of the diode. So in the back of my mind, I'm always checking my stuff just like this as I go. It's a little bit crooked. Now, the problem with this is if you're soldering it while you're grabbing those pins, you're going to have a very warm hand. Right? Now, I'm going to go ahead and do it, but what I'm going to do is I'm going to rest my finger on the pin that's on this side and not the one that's going to heat up here. Just so you realize what I'm doing here. Ow. I said I was going to do that, but apparently I was a little on both. All right, here we go. And with that, we've tested just about everything. Well, these are not soldered in, but I held them in there when we were doing the joystick work. And this, I'm going to just eyeball this one to make sure it's okay. The whole point of this is to be able to say, if I don't have joysticks, I can use these for general purpose inputs and have fun with that. Okay, so we should be able to generate interrupts now. it back on, make sure it's aligned. Connect everything back up. Plug in the power. LEDs are on, no smoke. It's all good. It's probably not any worse than before. That's always a good sign. Oop. Forgot to put a jumper on this header. I want to be able to connect up the interrupt, so I have to put this thing in. You generally want to make sure your power's off when you're doing this. This one you could do with the power on, but more often than not, you know, you get your pliers in here, you short something out or whatever. Don't be that guy. Okay, that looks okay. It's in. This thing is a little bit crooked because it's just too darn close to this thingy here. I'm going to have to do something about that, probably. There we go. It still boots. Not too shocking because the interrupts are not even used in the version of the BIOS that we've been playing around with to date here. Now to move on to test the interrupts. Now we've seen this before. We were playing around trying to get mode 1 to work. When we poke around with register 0 and register 1, one of the things we can do is we can enable the interrupts right here. We've already done the screen blank, shut that off. Want to turn on interrupts. Now let's make our code compatible while we're in the neighborhood with the other chip, because if somebody built one of these and it has a 9918 on it, we need to set this bit over there. Otherwise, our code is not portable, you know, because, you know, everyone's going to be using this stuff. So what does that really boil down to? Rather than setting this to 40, we're going to set it to E0. And that is going to get our interrupts turned on. And then once they are on, we should see the interrupt signal go active on the retro bus, which is over here on pin 16. Okay. Now, once that is happening, we saw another register down here. Register, is it 7 or 8? Yeah, here it is. This interrupt flag thing here, okay? The way this thing works, and there's a note in here, you can read and heed this note here. The interrupts, because they're level sensitive, what it means is that it'll assert the interrupt until something from the CPU tells the VDP to stop asserting the interrupt. And that's how it works, so that a CPU, it doesn't have to be looking at any point in time. It can't really miss them, okay? Them being the interrupt signals. So that it'll just assert it and keep it on, like a fire alarm, until somebody resets it. How do we reset it? We have to read this. So in order for us to put a scope on, which is how I'm going to debug this, onto the interrupt line on the bus, someone has to be reading this when the interrupts occur. Now, there's a few other problems here. In order for this to go, it's not going to handshake the way the Z80 or even the 8080 wants it to. It's just going to assert this interrupt signal. And I never designed a general purpose interrupt handler for the retro board, so this is kind of a problem for us. So what I'm going to do is not enable any interrupts on the Z80. And I'm going to write a program that just does a spin loop that reads this register waiting for this thing to go on, so that it will have been read then immediately afterwards, and then the VDP will de-assert the interrupt signal on the bus. And then when we put our scope on there, we should see the interrupt signal pulsing at 60 hertz or 30 hertz, depending on how often it does this. We're interlaced, so it really runs at 60 per second, but This is frame by frame, so it suggests that it would be at 30 hertz, because it puts 2 fields on the screen for each frame. Now, it really depends on how they define frame in this context. I don't know. It might actually do 60 hertz. I don't know. We're about to find out. Or I could read the rest of the manual, right? Let's just clip a scope on there while we're spin looping on this and see what it does. Always a satisfying sign when the machine actually boots. Let's modify our mode1.com program. This is setting the background color. Then we write it into register 7. We put 0 into address register 0. Then we put a 40 into register 1. So register 1 being this, that's what indicates register 1 there. So we're currently putting a 40 in there because all we did was write in that 1 bit to disable the screen blank. I'm going to just change it to an E0. Okay, so we're going to A110, a E0. So there's my E0 now. So I've got a background color. I put 0 into register 0. Put E0 into register 1. And then I go on my merry way back to the operating system. So once I've enabled interrupts, here's where I want to put my spin loop that just keeps reading the status register. The way you read the status register is you just do an in on port 81 from the retro. So if I go A118 in 81 jump 118. Let's just put some no ops down here to get the noise out of the screen when we disassemble it like this, so we can get a clear picture of what's going on. Fine. So we sit, there's my E0, and then I write into register 1, read back the status register, and go back and spin in this loop. Now this has to go pretty quickly. We could do this in DDT. Well, what happened is that DDT will run so slow in terms of because it's going to print out all this stuff on the screen. And what it'll do is it will not read this often enough to make the interrupt signal on the bus look clean. In other words, there'll be just giant, huge, long durations of that interrupt signal. But that will be asserted until this thing gets around to reading it again. That's okay, because we're not enabling interrupts on the Z80 right now for this test, and we're not using them for anything else. So this actually would be okay. Let me go ahead and save this so that if we crash, we at least have our data or our program here. So this is what mode1irq.com. Oops. Which is as long a file name as you can create on this thing. Now, if I DDT mode1irq.com, we have it saved. Okay, so if I just do a trace on this, it'll turn it on and it'll start going, and we'll actually be able to see the screen initialize. So let's do like a trace 1000 or something like that. Uh-oh. We crashed it, which strongly suggests that I forgot, and we must have interrupts enabled somewhere, because it just jumped off into This is why you save your work before you run it. Oh, this ain't good. I suppose it's good because we have an interrupt, I suspect. Let's see what the scope says it did when it got to that point. So our scope view here definitely shows that we asserted the interrupt line. That's for sure. And it seems to have seized when that happened. So I must have forgotten that I have interrupts turned on somewhere in the BIOS. So let's go have a look-see where and why that may be. I don't remember leaving it on. It's got to be in the BIOS because CPM is not going to mess with it. Enable interrupts. Yeah, look for EI, dang it. Well, that's, boy, there is no enable interrupts anywhere. How did it get turned on? You know what I could do is explicitly disable interrupts in our test program. That would do it. If this is what really is causing it to seize here. You know what else we could do? I could remove that header, the jumper. That way the interrupt signal will never go to the Z80. Then I could clip the probe directly on the VDP to see the signal going high and low. Then it won't cause anybody else to get upset about it. Now, I'm still kind of confused as to why this would crash it anyway. But this is certainly, it'll give us another clue. If it still crashes when we get down here, then that means something else is wrong, right? So this is a perfectly reasonable thing to do at this time. Let me pull the header off. Power's off. Grab a hook or something or a pliers to grab the little header and pull it out of there. The jumper, I should say. I keep saying header. These are jumpers or shunts or shorting block, whatever your terminology is. This probe here is still connected to the interrupt request line. I think that's perfectly reasonable. Let's rerun the test now. Nothing should happen at all. Even if this tries to assert interrupts this without the shorting block in place, they cannot go over to the Z80. So this should work now fine. Scope won't see any interrupts coming from this anyway on the interrupt request line because I've disconnected it. I boot it back up. Fire up our tester program again. We should be able to run this and it should just be able to spin. And when we read from the status register, we should just see the flag on all the time. Because no one's ever going to, well, it will actually go back off because it doesn't know that the Z80 actually saw or even cared about the interrupt. So yeah, this will be interesting. Let's see what it does. Well, it doesn't crash. That's a good sign. And what's happening here? We got a lot of garbage in the accumulators going nuts, actually. And when it's in this loop, nothing touches the accumulator other than when it reads this input port value. I should not have done it 1,000 times. Boy, that thing's going nuts. What else is in that status register that would change? Frame, fifth, let's see. Coincidence, fifth sprite number. Why are these bits all going nuts? Well, let's look at the frame flag. That's the most significant bit. It's on and off and on and off, which is what we would expect from time to time. Actually, we would expect the frame flag to always be on if we do this at manual speeds. Because if it's going super fast in a loop, it could read it faster than it takes to redraw the whole frame. It's definitely on all the time. And other bits are a-changing. So that means it's recording weirdness in this 5th sprite number. I mean, those least significant bits are going nuts. Since we never really initialized this thing, and we never configured the RAM in any way, I haven't even read the manual on how any of that stuff works just yet. I've skimmed it over. It may mean that all the sprites, from the perspective of the VDP, are like all in the upper left corner piled up on top of each other or something like that. And it might very well mean that they are having too many on the same line situation, and it's just simply reporting that all these sprites are on top of each other. It doesn't mean we have an actual problem, the fact that these bits are changing. It just means that I haven't read the manual, don't understand what they mean. What I do know is the most significant bit is pegged on right now when I do this manually, and it goes on and off and on and off again a little bit when this is spinning in debug mode. Now, if we get out of the debugger and let this spin at full speed, once it starts doing this, it's going super duper duper fast. And then when we put the scope probe on there, we should see it'll jitter in its width. But when it asserts an interrupt, it should go back off in the amount of time it takes it to go around this loop, depending on what it's doing at the point in time as it goes around this loop, when the interrupt is first asserted. I think that's our next test. All right, so for this test, we're going to use one of these. This is well, let's power it off first. All right, LED's off. This allows me to get a probe clipped onto the pins of one of these chips, and it just clips on top of it. I think you've seen this on my channel before. All right, so I'm clipping it on the bottom half of the VDP because the interrupt line, I don't know, it's down here somewhere. We need to go back to the data sheet and find it. And we find that it's on pin 16. So this is pin 20. So then we've got 19, 18, 17, 16. It's right there. Now, this should be going on and off. If we run at full speed in our spin loop. Powered on, that's a good sign. Now keep in mind, as I understand it, the output of the VDP chip on the interrupt line is not open collector. Therefore, we should not need to have a pull-up resistor on that pin. And that's why I added this diode down here so that it made it look like an open collector. Okay. Now, if we look at the scope, we see a little bit of noise. It's basically a high signal not asserting any interrupts right now. And that makes sense when it comes out of reset. Hopefully, it would be nice if it initialized itself with interrupts disabled. Okay, we're booted back up again here. Now, if I just simply run mode 1 IRQ at full speed, fingers crossed, it initialized things, and this should... It's in a spin loop, so it shouldn't be doing anything that we can see right now. And if we do a couple of random captures with the scope, we can see that, yes, it's jittering in its width up to about a microsecond, which is not too shocking. So that's probably the loop rate, speed of those instructions, since the jump takes quite a few cycles to fetch all the bytes and so on. And this strongly suggests that things are working the way they're supposed to be working. And that leaves us with the massive head scratcher, which is, why does my code fail when it asserted an interrupt, when the VDP was asserting the interrupt line, even though I believe that interrupts are disabled. Well, there's a couple of clues. Now, DDT does not enable hardware interrupts. But, in a related note, this is the low memory. We can look back a year ago when we were starting to work on our BIOS. It tells you that this is the CPM manual, of course. What are all the bytes used for in the bottom of memory? And it says here's the interrupt vector locations 1 through 5 not used, 6 is not currently used but it's reserved, and 7 contains a jump instruction to the DDT or SID when it's running. And when it's running in debug mode for programmed breakpoints, but is not otherwise used by CPM. Now, we were running DDT. We were doing tracing. I don't know what it means to have a program break. Well, I do know what a breakpoint is. In DDT, you can say run and then stop when you get to some instruction X. And what DDT does in order to stop it there is it puts a restart 38 instruction in that place so that it runs it. And then when it gets to restart 38, it'll go to do this restart. What the 8080 calls restart 7. And what the Z80 calls restart 38, what it does is it branches to address 38. So that might be a thing, but I'm not buying it really here. What's more likely is that I turned on interrupts somehow and forgot that I did it, and they need to be shut back off. So let's reboot and tweak our program a little bit. DDT mode 1 IRQ.com. What I'm going to do is I'm going to just start down here at 120 and type in disable interrupts, and then I'm going to say jump to 100. Now the problem with this, of course, is I won't be able to run it from the command line, which is ultimately what I want to do. But let's at least do this now. I can do a disable interrupt, then go up here, come down there, and then go into my loop. This will run with the debugger going. And with hardware interrupts disabled, they shouldn't crash the system. And now, of course, I did all this, and I need to put that header back in. We can sort of do that while it's running. I don't want to do that. It's not going to happen. This is a bad idea. Save one mode 1i2.com. All right, let me reboot it. And all right, power down, put the header on, and reboot it. What did I call that? Mode I2. So if we just say XP120, oops, XP120 like that. And then we just do our trace. It'll start here and it'll go round. Let's see how far it goes though. Trace, I don't need to go that far. And we croaked again, ladies and gentlemen. We did disable it. We go around here. Boy, this is very strange. I did not expect this at all. Wow. Wowie, wow. This could happen quite easily if I accidentally hooked it up to non-maskable interrupts, but let's double check that I got the right pin here. I assume this is right. Interrupt on pin 16 comes to this header here. It goes to the diode, goes over there, up and around. Boy, what the heck is that thing doing? Oh, that is where the pin 16 is on the VDP. I forgot this chip was in there. Okay, this looks okay. Let's go back to the retro and make sure I know what I'm doing here. I got int NMI. NMI is on 17. Well, none of the other stuff here would have worked in any sane way if I screwed this up. And who knows, you know? I screwed up the DRAM. So int 16 NMI 17. Let's look at the manual. Int 16 NMI 17. I would crap if I got that wrong at this point. Of course, it doesn't mean this is correct either. But I am very confused. If interrupts are disabled, it should not be relevant in any way what's going on over there. Wow. There's a head scratcher for you. Well, what else do we know? We know that when the Z80 boots up, no one has configured any interrupt modes. The Z80 is in mode 0 when it boots. If we go back to the manual and we search for mode 0, reset, blah, 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 INR sets the interrupt status to mode 0. Mode 0, blah, blah, blah. This one tells you what it does when it gets an interrupt. Mode 0 does what the 8080 does, and yada, yada, yada. This says that you're supposed to send an interrupt acknowledgement phase where the peripheral device inserts an instruction onto the data bus that will be executed by the CPU in response to the presence of an interrupt. Mode 1, the CPU will always just execute a restart 38, which is unfortunate because if we're in debug mode in DDT, it's going to clobber the address for that vector. Mode 2 is the one that we've seen in the past. This is the one that I use when I was testing and playing around with the SIO and the CTC. I was assuming that when we're playing around with video stuff, if we don't need the timer interrupts and the SIO, we can use mode 1 to synchronize ourselves to the VDP. Right now, I'm thinking a real serious head scratcher. Now, we can actually generate interrupts if we want to. If I put a return from interrupt instruction at address 38, then anytime there's an interrupt, it'll immediately go in there and come back out. If the regular program running is going to do something like this, the spin loop over here, that that won't work either because it'll get another interrupt right away and keep going back in, and it'll go into an infinite thing there. So what I really need to do, if I go into mode 1 and address 38, I simply put in 81 to read the status register, and then I do a return from interrupt. That would cause it to react to the interrupt by reading the status register, and then the VDP would shut that off. That should work. But this still doesn't explain, in my opinion, why the thing is down now. That is, I don't know what's going on. We may have to get more creative. We might have to do some more bus probing to see what's going on. Wait a minute. If I let my oscilloscope free run, I'm in a spin loop of interrupts right now. Well, that makes me feel a little bit better. But now I'm super duper duper confused because who's reading the status register to reset that interrupt line right now? Wow. I'm in the deep, but yeah, this is very strange. Very, very strange. But let's get one more piece of evidence. Let's reboot it again. Let's not do the disable and the jump and just free run it without this and see if I get the same results on my scope. All right, so it's going to go in here and then it's going to go Spin around in that loop. Now we can trace 1000. We don't need 1000, we just need 10. It initializes and seizes. Wow, now I'm really confused. The scope is pegged to ground and stays there. Now I'm so confused. I don't know what I don't know what the heck is going on. If I disable interrupts and then do this, someone somewhere is reading the status register in a loop. I suspect we're looking at something going on with DDT here. I'm not so sure here. Let's go back to this. All right, so what I'm going to do is I'm going to rewrite this thingy with some space at the top. I'm going to disable interrupts, do all this, and then go into spin loop, and then I'm going to run it without using DDT, and I'm going to hope that it will do what we expect it to, and that is read the status register in a loop and get the jitter that we just saw on the scope that appears to be happening miraculously on its own, with DDT seized in some strange way, doing something that I have absolutely no idea what's going on. Very, very, very weird. So if I say assemble, well, we can do is A100. So let's just do a couple of no ops. Oops, keep some room for future growth here. And then we'll just type the same program in we had before, MBI A1C, out 81. Yeah, this is going to go well. MBI A. You know what? Why don't I actually go back and read this stupid doc? Find out how to move memory in DDT. Well, I used to be good at this, you know. Alrighty, the assembler, DDT, the M command, page 74. Of course, this is probably not clickable. Okay, LD, ed. We're on page 67, so there must be the, not accounting for the table of context, table of contents. An example. Come on, where's page 74? Hello. There we are. Trace command. Beware, this will screw up your program. No, I'm just kidding. What the heck is going on here? Read, move, block, move. Source FD. From source. Final address. Destination address. What the hell? Start. Final. Destination. Oh, I see. This S and F, that's a range, and D is the target. So when I did it the first time, I just moved God knows what to who knows where. First moved from S to D, and both addresses are incremented. If S exceeds F, otherwise. So it tells you this so that you know this is a destructive move. So, yeah, so by that, I mean this. Here's our program. So what I really want to do is just move this down a little bit. If I try to move, you know, all this from 100 through, you know, whatever, 119 to 102, it's going to do what we call a destructive copy. Let's wreck it just for example, 100 through, let's say, 120 to 102, right? Now we say L100. And that's a destructive copy because it copied it in before it saw the value. So if you really just want to move it down a little bit, what you need to do, you just move the whole thing off into nowhere, and then you can move it back again. So if I say move 100 through 120 to 200, because I'm not using that memory at address 200, then I can say move 200 through 220 to 110. All right. So we should see the program, a copy of it starting here at 110, with this is the original stuff up here. Maybe a little confusing, okay, but deal with it, all right? So at 110, we should see our full thing here, right? 1 sees foreground, background into register 7, 0 goes into register 1, 40 goes into register 1. What am I doing here? I'm not reading it correctly. Boy, this, yeah, even as I'm having a hard time with this. Anyway, the program now starts here. I'm going to no-op all of this stuff out, okay, which I can use the F command to fill something, right? It's got to be up here somewhere. The I command, R, F, S. I'm inclined to take a wild swing at it without reading the doc, but, you know, I messed up the move. Let's see here. I don't know if it's fill address and length or if it's, yeah, from and F, S start. Okay, so this is the from and the to and the value. So it's not just address and length. So let's go ahead and let's fill 100 through 1 OF with 0. That's the opcode of a no-op. So now this will make more sense. This is what I intended all along with the big move. Okay, so I made a hole up here, and now we can say foreground, background into register 7. Put a 0 into register 0, and a 40 into register 1, and we're done. Okay, fine. We're back to the where it makes sense. A100, let's disable interrupts. Okay. Then it'll fall down into this code down here. We'll put our spin loop down here. Let's say assemble 128. VI. Oh no, we actually just want to say input 81. Jump 128. Put some no-ops here to get the noise out of the way. All right, 128. Interrupts are disabled. Now, we don't want to put this 40 in there. We need to fix that. Remember, we want to put E0 in there. Oops. MVIA, comma, E0. Instead of 40, and we want to write that into register 1. And we want to do that because that's going to turn on the, oops, we were almost there. Interrupts this and the right memory. Okay. Let's go ahead and save this since it'll probably die again. Now, one page is 256 bytes, which is 100 in hex. This whole thing still starts at 100 and ends before it gets to 1FF or 200. So that's still one page. So this is going to be our new mode 1i2.com command. Now, if I run this in DDT versus on the command line, mode 1i2, I believe this is supposed to generate what we just saw with the chattering interrupt signal on my scope. And indeed it does. So I believe all this foolishness adds up to the fact that if you're in DDT, you really don't want to play around with interrupts and stuff like that, because who knows what's going on. I'm very confused. Maybe somebody's got some insight. I don't enable interrupts in my system. And you even saw me disable them. Hardware interrupts in the DDT code. And we went into the loop. And yet, weird things happened. In fact, weird things so much so that I can't explain why the trace mode of DDT stopped functioning. Let me reset and do it again. I mean, think about what we saw there, right? This is what we just ran at full speed, and this behaves exactly as I would expect it to. CPU is ignoring all interrupts, doesn't care. This is going on like crazy, and we get the interrupt signal in the same way. We expected a jitter. Newsflash, your interrupt is always going to jitter when it's level sensitive, and you have to wait until you get your handler, because it could always take a little bit different amounts of time. And in this case, of course, we ignore them at all, and it's still just spinning. So again, it depends on, well, you could call the phase angle in this loop that the instruction execution is at when the interrupt arrives. I just am really bothered the fact that I can't trace this without it stopping there. Anybody, can you explain this? Disable interrupts. Who actually re-enabled them for real? DDT is not going to do that. It just doesn't make any sense at all. I'm in mode 0 right now, so if there was a real interrupt and it was acknowledged, the thing would just crap out. I believe I'm in mode 0. It could have been set to mode 2. Let's have another look at the retro BIOS. I'm just freaking out here. This is not what I want to do. .asm maybe. Does anybody ever even change the mode of the CPU? No. Actually, the command is im, not mode. Mine is ignore case im star.asm. Now, CPM is not going to do this because it doesn't care about hardware interrupts. There's my retro BIOS, and then here's the comments from all the different cache modes we've been playing around with. It just doesn't happen. Do I do it in here? I wonder if I'm building in some clock logic or something. Because this does mess around with interrupts. We got interrupt tables in here. Wow, it's interesting that I don't have IM instruction anywhere. I would expect it to be in here. Enable interrupts. Anybody? Here we go. No. Here we go. In CTC3. EI timer mode. The only place I actually have an enable interrupt instruction is in CTC3.asm. So let's see if I forgot that I'm using that for something in my retro BIOS. Go with a no. Is it in anything, anywhere? It's in the dock for CTC3. CTC3.asm is not included, nor used anywhere. I can be more aggressive about my grep. Grep -R. This, does it occur anywhere, anyhow, for any reason, in any case, upper or lower case? Now, I'm reading a lot of data, and there's binary files and all kinds of other stuff in here. Nobody know-how uses this file right now since I've been playing around with debugging, I'm sure. Anybody? This one, yeah. No, I don't have an, not off the top of my head. This is one of those things a week from now I'll wake up and I'll go, aha, yes, suddenly I remember that on odd-numbered Saturdays, this happens. Oddly enough, it is an odd-numbered Saturday as I'm recording this. Oh, my gosh. Weirdness abounds. So the weirdest thing of all is once I enable the interrupts on the VDP, and this thing seizes, I can see on my scope that someone is executing this loop at full speed without any trace dumps coming out of DDT. I just know, I mean, with hardware interrupts, I don't buy for 1 second that they've become enabled somehow. I'm not even operating in the right mode, being mode 1, as we saw a minute ago for the CPU, for it to act the way it is, if interrupts even were enabled in the first place. There's got to be something goofy going on with DDT. As even so, if I trace 100 right now, it gets right here, and now the scope is chattering as if DDT simply stopped tracing it with a register dump, and it's running at full speed without a register dump. It's the only way this could possibly happen. I'm really not in the mood of debugging the debugger. I'm going to look the other way for now and declare this as working and consider this an anomaly of the debugger. I would love to hear if anybody can explain this one. Let me know in the comments below via Patreon or any other way that you have to communicate with me. I would love to know the answer to this question. Why is DDT not printing these traces out when nothing in the system is enabled interrupts? I explicitly disable them when they're not used anywhere in this build of the BIOS. How in the world has the tracing stopped while the reading of the port continues at full speed? Well, I guess the upside of all this is while I can't explain why the software is doing weird things, the hardware is working exactly as expected. So I'm going to call this a success, generate the Rev 1 Gerbers, order the board, and move on to build and test that one. I'll worry about the software problem later. So again, if you got any explanation for this weird software behavior in DDT, let me know. I'd love to hear it. Thanks for watching. I'll see you next time.